Marshall Burke is our guest today. He's an assistant professor in the Department of Earth System Science and a Center Fellow at the Center on Food Security and Environment at Stanford. A great place to be to do environmental work, as his principal, of course. His research focuses on social and economic impacts of environmental change and on the economics of rural development in Africa. Marshall holds a PhD in agricultural and resource economics from Berkeley and a BA in international relations. Marshall is another one of those young people with an omnivorous intellectual style. He's just eager to solve many loosely related problems at once, and he's going to give us a grand synthesis one of these days, I'm sure. What he's been particularly adept at is borrowing and developing tools from a wide range of disciplines to investigate human welfare and livelihoods, particularly in the context of climate change impacts. He's one of the leaders in application of econometric tools to the climate change arena. The impacts arena had stagnated a bit in terms of methodologies until a couple of scholars about 10 years ago, followed by an influx of brilliant young investigators, including Marshall and our former postdoc here, Saul Shung, essentially struck intellectual gold by taking a cue from Michael Greenstone and a couple of others in combining climate and econometric techniques to give us a new view on climate impacts. Today, Marshall will be discussing new evidence on the economic impacts of climate change. Please join me in welcoming Marshall Burke.
All right, great. Arc seat, yeah, sorry, the black background. I went for something ominous given the times. So thanks a lot, Michael, for the nice introduction, and thanks for having me out. And apologies for the generic title. I sent this a long time ago, and so it's a title that doesn't really say too much because I wasn't sure at the time. This was like 6 months ago what exactly I wanted to talk about here. So I'm going to tell you about a few new research projects we have going on, and these are projects with a bunch of collaborators who I should acknowledge. Some postdocs who work with me, particularly Sam Burke-New, and also Saul Shung, who I continue to work with, who Michael mentioned. So yeah, again, I was disappointed in this generic title, so I went, in the last week, of course, given recent developments, looking for some inspiration from the media, right? So here was the New York Times article that you guys might have seen from a few days ago. Donald Trump had put climate change on the course for quote-unquote danger zone, right? Good quote there, danger zone. Where did that come from? Turns out it came from our own Michael Oppenheimer here. So if Trump steps back from that, and I think that here was the clean power plan, it makes it much less likely that the world will ever meet that target, 2-degree target, and essentially ensures we will head into the danger zone. So given that, let me try a new talk title here, A Statistical Voyage into the Danger Zone. Okay? So I'm sure folks have seen lots of talks on climate impacts in this area. This is an area, where there's been a lot of work recently, but I think an area where there's still a substantial amount where we still sort of don't understand and need good work. Either of the statistical variety I'm going to show you, or many other potential varieties. Okay, so I think it's useful to start very big picture, and again, I'm coming to the world from economics here, and I should mention I'm also used to economics audiences, which tend to be very rude and blurt out questions sort of whenever they feel like it. So if people don't start blurting out questions, I'm gonna feel uncomfortable. So questions or comments at any point, please. Economists have been interested in this topic for a long time, as have other folks, and a lot of what our discipline thinks is going on here in terms of climate impacts can be summarized by this graph. Okay. This figure plots damage functions, so estimated relationships between future change in global temperature in degrees Celsius, so that's on the x-axis here. This thing works, yeah. And in this case, percent change in global GDP. Okay, so think of this as a summary measure of the global economic impact of climate change. And this is for future warming relative to pre-industrial, right? So right now we're at about at 0.8-ish relative to pre-industrial, relative to, let's say, the 1800s. And as we crank up the temperature, this is what 3 different integrated assessment models suggest will happen to global GDP. Okay? So what do they say? They say up to about 2 degrees-ish, we're all right, and then after that, things start to slowly drop off. And depending on who you are, if you're Richard Toll, you're up here. If you're Nordhaus, you're a little bit lower. But at about 3 to 4 degrees, we see impacts of, let's say, 2 to 3% global GDP. And this is relative to a world that didn't experience climate change. Okay? So 2 to 3% impact for 4 degrees warming, right? This is 4 to 5 degrees we think of as sort of the RCP 8.5, the unmitigated warming scenario, sort of the most likely outcome, right? So 2 to 3% for RCP 8.5. Okay, so let's think about that number. Is that a big number? So consider an economy that's growing at 1% a year, right? So we're in 2016 today. Let's say we grow at 1% a year until 2100, okay? That economy, through the miracle of compound growth, is going to be about 132% richer in 2100, okay? So taken literally, what these numbers tell us then is with climate change, instead of being 132% richer, we're going to be 128% richer after 85 years, right? Or put another way, you're going to reach the income we would have had in 2100 just a few years later. We're going to reach it in 2102 or 2103, right? So who cares? That doesn't seem like much, right? So, and I highlight this is because this is literally the estimates that are being used by the EPA right now. And of course, this might change. They might not be using any numbers soon, or they might not exist soon. These are the damage functions that are being used to estimate the social cost of carbon, the literal number that the EPA and institutions around the world use to understand the aggregate economic impact of climate change, right? And that's what it is. Okay. So, is this number right or not? These things were built for the most part 10 to 15 years ago, sometimes older. DICE, the original DICE was written back in the 1990s, right? And so there's been a lot of worries that these damage functions don't really summarize all of the potential impacts of climate change, right? And a lot of grumbling from many different quarters about trying to sort of understand and come to terms with these numbers and figure out whether or not they're right. Okay. So let me sort of highlight some conventional wisdoms in economics, and I think sometimes more broadly, that are baked into the numbers I just showed you, right? Some of these are explicitly baked into these integrated assessment models, as folks know who have worked with these. And some are sort of inform the damage function estimates that you see in these models. Okay, I think there are 3 important conventional wisdoms, at least 3. So number 1 is the intuition, and this is very strong in economics, that there's something about being a wealthier country or a wealthier individual that insulates you from the effects of environmental change, climate change in particular, right? So again, this is explicitly built into some integrated assessment models. So for instance, FUND allows countries, the damage function to decline as countries get richer over time. Richer countries are just better able to deal with this sort of thing. Okay, so that's number 1. Number 2, at a related point, societies tend to adapt their environment over time. So as you're exposed repeatedly, let's say to hot temperatures, you sort of figure out what to do. You start to anticipate it. You behave differently in a way that mitigates some of the impacts, right? Sounds intuitive. And number 3 is agriculture is probably our best studied sector in the climate impacts world. And so a conventional wisdom that's around is that we think agriculture is sensitive, but we don't think many more sort of modern industrial sectors of the economy that are important to countries like the US, we think these other sectors might not be that sensitive, right? So you sort of roll up these 3 conventional wisdoms, and they help inform the sort of damage function estimates that I showed you before, right? Which show on a global level impacts that maybe aren't necessarily that big. Okay, so for today, I want to think about these conventional wisdoms, and again, think about this broader picture of the climate impacts, explore the danger zone, if you will. But think about it in terms of a sector where we think impacts could be really large, but where, particularly in the developing world, but also in rich countries like the US, where our understanding of potential impacts is still pretty poor, right? And this is in the health sector, the health domain. Okay, So here's this is a plot from the recent Risky Business report, the American Climate Perspective. So this is done by Saul and Bob Kopp and a bunch of folks around the country. Basically, it was a study looking at the U.S. and trying to do a ground-up estimate of what the aggregate cost would be. So instead of taking a top-down approach, just looking at sort of GDP impacts, we're going to go sector by sector, and then we're going to add up all the sectors. That's basically what they do. Okay, and so what do they find here? This is, I won't walk through all of this, but these are the different sectors. This is sort of sea level rise, this is agriculture, this is labor productivity, this is crime, so we see some increases in crime as you crank up the temperature. This is mortality. So people have known for a long time that during heat waves people die in the US and around the world. It turns out that you can add all of these things up and the impacts are still much smaller, or I think that the combined impacts here are smaller than what you get if you dollarize the value of mortality losses, right? So we think people are going to die as you crank up the temperature. Us as individuals are willing to pay a certain amount to not have that person die, right? So this is called, in economics parlance, a value of a statistical life, right? And this is a sort of an odious idea to some people, but it's used all the time and explicitly used in U.S. governmental regulations deciding whether we build a guardrail along a highway, right? We need to understand what's going to be the benefit of that, right? And we value benefits by this, again, this value of a statistical life. So the current value that's used by the EPA is like $8 million, so human life is worth $8 million. So what you can do is you can take an estimate of how many people we think future warming temperatures are going to kill, and you multiply that by the value of statistical life. And that, as a percent of GDP, dominates the sectoral impacts everywhere else in the economy. All right? Yeah?
You're using the same VSL in all the countries around the world?
Well, that is a great question. So this is just for the U.S., and it's just using the U.S. VSL. So there's a whole fraught economic and ethical literature around the VSL and whether it should differ across countries. So basically the VSL is calculated by your willingness to pay to avoid death. So how much am I willing to pay to buy a bike helmet, right? Well, if I'm rich, I might be willing to pay a lot to buy a bike helmet. That reduces by epsilon the probability of me dying, although on Stanford campus it's probably more than epsilon. People don't bike very well. And so I can calculate by dividing how much I paid by the difference in probability of dying, that's sort of my willingness to pay to avoid death, right? That's clearly going to go up the richer I am. I'm willing to buy a nicer bike helmet. So as Denise points out, in poor countries that number is going to be a lot smaller, right? Just because people don't have the money to spend on a bike helmet, right? So you get different VSLs based on income, and that clearly has some ethical issues. So right here, this is just using the US VSL, which is like $8 million. Okay, my point here is that the dollar value of mortality impacts, by this estimate alone, is roughly equal to the sum of all other projected impacts in the U.S., right? So health could be really important. Okay, this is in the U.S. where we have pretty good data. So let's think about these conventional wisdoms in the health context. Okay, so here is sort of the key quote, or a key quote from the last IPCC assessment, the fifth assessment. This is the working group 2, so the impacts group chapter on agriculture, chapter 11 for those scoring at home. Folks in here, I'm sure, contributed to it. So here's the quote. Impacts on health will be reduced but not eliminated in populations that benefit from rapid social and economic development, particularly among the poorest and least healthy groups, right? So again, this wisdom is as we develop, we're sort of less sensitive to climate impacts. Okay. So let's think about that in the U.S. first and then in developing countries. So I think in the U.S. we do have some pretty strong evidence that has something like that has been going on. So you've probably seen plots like this before. This is the relationship between all-cause mortality, so mortality from anything that could kill you in the U.S., and exposure to temperature in different temperature bands. And so sort of no matter where this has been done, either in the developed world or in isolated places in developing countries, you see this U-shaped relationship, right? People die at increasing rates when it's really cold and when it's really hot. Okay? So this has been sort of known for a long time. This is a paper from Duchesne and Greenstone from a few years ago. There's now a few papers on this in the econ literature and many more outside the econ literature. But what's interesting here is this relationship. So take this coefficient, right? This is the average coefficient over, 30 years, right? We have pretty good mortality statistics in the US, so we can plot how this coefficient, the mortality response to really hot temperatures, changes over time. And what they show, this Burke et al. Paper, which is really nice, what they show is this relationship. So take this coefficient and we're going to plot this coefficient over time, right? So back in the 30s and 40s and 50s, it's pretty high, and it's come down fairly dramatically, fallen by about 75% over the last half century, right? So what that means is we've become much less sensitive in the US to high temperature exposure in terms of all-cause mortality. Again, looking at all the things that can kill people, right? So that seems promising. Similarly, the one developing,
That's ambient temperature.
this is ambient temperature, this is just like, these are county level data, basically. So I calculate the mortality rate, or Allen and company calculates the mortality rate in Santa Clara County in California, where I live, and relates that to the ambient temperature in that year in Santa Clara County. Okay? Yeah, so just ambient temperature. Okay, so there aren't too many developing country analogs of this study. There is one in India, and basically take that U-shaped response function I showed you before. So here's the sort of US one in blue. It's squished down for a reason that will become obvious in a second. And that reason is we're comparing it to the same mortality response in India, right? And that's the red line here. So in India, there actually are pretty good mortality statistics back for about half a century, at least at the sort of province or district level, so you can run the same sort of analysis. And what they find here is, again, in this hot bin, the effect of a hot day in India is about 10 times as large as the effect of a hot day in the US, okay? So again, some sort of income adaptation story, right? The poor country here seems maybe less adapted to hot temperatures than the US. Okay, and a lot of different stories you can tell for why that might be true. So let's think about those stories. What's going on here? Okay, I am not a medical doctor, as is obvious. My wife's in the medical school, so she and her colleagues sort of laugh at slides like this. And I actually showed this, made the mistake of putting up this slide in a talk to some global health folks the other day, and it was cringeworthy. Here's my economist understanding of what might happen when you crank up the temperatures to humans, okay? A lot of different things. So the sort of direct effects, just think of this as heat stress, heat failure, right? So your body gets really hot, organs start shutting down, that leads to death. But there are a lot of other channels we might be worried about. So another one is food, right? We know hot temperatures lower agricultural productivity, and that could affect health outcomes through nutrition, right? Similarly on water. As you crank up the temperature, you get increased bacterial production. Again, this could lead to many health outcomes that we care about, negative health outcomes. Air, folks, so there's this relationship between temperature, this nonlinear relationship between temperature and ozone formation, right? So temperature could cause health impacts through its interacting effects with other things that are in the atmosphere. Temperature, this is again medical terminology here, temperature is associated with flying and biting things that we don't like, right? Mosquitoes often change their range as we crank up the temperature. And finally, and we've worked on this some, temperature also, it turns out, affects how humans interact with each other. So you crank up the temperature, and the data show in a lot of different settings that you see increases in various types of human conflict. Okay. So here's a laundry list. Maybe you can think of more that are on this list. So as we think of wealthier countries, again, thinking about adaptation, there are a couple of these things that we can sort of cross off the list, right? We worry less about sort of food insecurity in this country, although it's not entirely true. Our water systems work pretty well, right? So we have ways of dealing with that problem. Flying, biting things, for the most part, we don't have too many people dying of malaria, dengue and Zika. Now it's sort of, that's changing. But for the most part, right, being in wealthy countries, you don't have to deal with a bunch of these changes. That's good. Okay, so being wealthy eliminates some of the channels, but I'm going to show you evidence, and again, this is from a new project, that suggests that there are very important channels that it does not eliminate, and channels that we still don't really understand that well. So here's a pop quiz. I didn't know you were coming for a quiz today, but and I think this is even true, of the top 10 leading causes of death in the US this year, what is the single cause for which the mortality rates are not declining? So think of the 10 most likely things to kill people in the US. Which of those 10, and there's only one of them, our mortality rate's not going down. They're actually going up.
Guns.
Anyone know?
Guns.
Suicide. So it's suicide. It also might be Alzheimer's now, but the age adjustment sort of affects that. So suicide, it's clearly true for. So here are the age-adjusted suicide rates in the US, just over the last 15 years. Sorry, this is unreadable. Here's the total effect. So men are much more likely to kill themselves than women. Actually, they're much less likely to try to commit suicide, but they're much more successful when they do commit suicide, typically because they use firearms. So they're actually 4 times as likely to be successful as females in committing suicide. But overall, rates of suicide have gone up by 20 to 25% over the last 15 years. Okay? So large increases in suicide. And this is particularly true. It's the leading cause of death, or one of the leading causes of death, among people my age, among sort of younger people who aren't yet dying of other things. Okay. Suicide is also more broadly related to mental health, as we know. So depression is implicated in something like 90% of suicides. And it turns out depression and mental health status is the leading cause of global disability around the world, right? So not only do the consequences, so suicide is one manifestation of poor mental health. There's often people who don't commit suicide who live for many years and live with disability because they have mental health. And it turns out that they have poor mental health. And it turns out poor mental health is, at least according to the global burden of disease, who comes up with thoughts like these through some sort of statistical black magic, mental health is really important. Okay, so why do I bring this up in the context of climate? So as folks in here might or might not know, people have long sort of noted and been interested in the relationship between the climate system and suicide. So the earliest known writing we could find about this was from this German physiologist, Casper, I forget his first name, who wrote about this and particularly noted the seasonality in suicide, right? So what people have long recognized is in Northern Hemisphere, you get this strong spring-summer peak in suicide. So suicide rates are much higher in May, June, July than they are throughout the rest of the year, okay? So 1825 was the first known discussion of the suicide seasonality. And what do we know about the seasons? So in the Northern Hemisphere, those are the warmer months, right? So there's this clear sort of seasonal pattern that might have something to do with temperature. Next time this was written about was 1897 by Durkheim, who was sort of the father of modern sociology and much of modern social science. He too recognized the seasonality, but was actually worried about omitted variables. So here's a nice discussion of omitted variables as early as 1897, right? So he says, sure, temperature varies seasonally, right? But a lot of other things vary seasonally as well. So temperature is going to be correlated with other things that might also affect patterns in suicide, right? Okay, so what we want to do is think carefully about these omitted variables in sort of a modern statistical setting. So we have good mortality data from 2 countries. We have it in the US, as I just showed you. At the county level, and we know cause of death. So the U.S. mortality statistics give us a really good sense of sort of why people died. And there are many different data sets you can use in the U.S. to do this. So I'll show you a couple of them. We also, working with a graduate student, we also scraped a bunch of data from the Mexican health statistics. So we have mortality statistics at the municipality level in Mexico since 1990. So something hundreds of thousands of municipalities in Mexico. And we have annual mortality data, including cause of death, for these municipalities. So a really nice data set. So what we're going to do is take the sort of standard statistical approach that Michael alluded to earlier in his introduction. So we're going to, the thought experiment is this. So let me take Santa Clara County, where I live, as an example. You don't want to compare Santa Clara County to neighboring San Mateo County or another county in California. Right? Because those counties differ for a lot of different reasons, and they might differ in ways that also affect people's propensity to, let's say, commit suicide, right? So it's very hard to compare, let's say, Santa Clara County to an inland county, Kern County in California, just because they differ in a lot of different ways. So our statistical approach instead is to use Santa Clara County as a control for itself. So we can take Santa Clara County on a hot day and compare it to Santa Clara County on a normal day, or in a hot year versus a normal year, right? And in that sense, we think we've dealt with a lot of the omitted variables that you might be worried about, that sort of plague these cross-sectional comparisons. And we can do this for all counties in the U.S. or all municipalities in Mexico, and we can sort of aggregate up the effects, and that gives us a sort of an overall estimate of, in this case, the effect of temperature variation on suicide, on successful suicide in the U.S. and Mexico. Okay, everyone, hopefully I'm happy to talk in boring detail about what actually goes into this if anyone cares, but hopefully that's clear. Okay, so what do you get when you do this? Sorry, you guys can't quite see the confidence intervals here. So here's the U.S., here's Mexico. We're again relating changes in the monthly mortality rate due to suicide to exposure to daily temperature in different bins. Okay, so a couple things to note here. You can't see the confidence interval, but these are very tightly estimated. So in both the U.S. and Mexico, hotter temperatures increase suicide rates. And unlike that all-cause mortality relationship I showed you before, which was a U-shape, pretty much anywhere we can look at this, and we can look within these countries as well, we see this nearly linear upward sloping relationship, right? So hotter temperatures increase suicide if you're a cold county or if you're a hot county. If you're a cold county or a cold municipality in Mexico, or you're a hot municipality in Mexico, right? So suicide increases linearly with temperature. So already that suggests, if you sort of believe that, we can beat this up in many different ways, and we find this linear relationship. This already sort of suggests a different mechanism than the all-cause mortality effect that I showed you before, right? Which was this really strong sort of U-shaped relationship. Okay. So let's think about that then in terms of the conventional wisdoms we talked about before, right? So again, number one, rich are less susceptible than poor. Number two, people figure out how to adapt as they're exposed. And number three, effects decline over time. So we have multiple decades now in 2 countries that allow us to explicitly test these conventional wisdoms in the context of this outcome that we care about. And sorry, this is a horribly boring and data-rich slide here that you also can't read. So let me take you through it, or parts of it, in testing these conventional wisdoms. So first, let's test whether rich are less susceptible than the poor. So we can do that by comparing the U.S. and Mexico, or we can do that by comparing rich places in the U.S. to poor places in the U.S., or rich places in Mexico to poor places in Mexico. And when we do that, we basically find no difference. So the U.S.-Mexico estimates are actually not statistically different. We can't reject that the effect is the same in the U.S. and Mexico. We can't reject that richer Mexicans are less likely to be affected by climate than poor Mexicans. In the U.S., we actually find strong statistical evidence that this effect is much larger in wealthy counties, which is something that you talk to epidemiologists who study this stuff, and they sort of nod their head. I think if for some reason it makes sense to them. Suicide is often, we see high suicide rates among wealthy populations, and this has been sort of observed for a long time. And similarly, we see large effects of temperature on suicide rates in those populations. So at least in these 2 countries, we find very little evidence that income is a mitigating factor in the effect of climate on this outcome. Okay. Second conventional wisdom. People more frequently exposed to hot temperatures figure out how to adapt. Okay, our simple approach here is to compare hot places in the U.S. to cold places in the U.S., or hot places in Mexico to cold places in Mexico. And again, what we find doing that, sort of a simple comparison, we find no difference between those 2 things. So if you live in Phoenix, Arizona, and the temperature goes up by 1 degree Celsius, you're just as likely to commit suicide as if you live in Fargo, North Dakota, statistically speaking. Same thing in Mexico. So no evidence that being exposed to hot temperatures somehow helps you adapt over time. And also we can plot this decade by decade, and we see no decline in the relationship over time in the U.S., and actually a small increase in the relationship over time in Mexico, right? So at least for this outcome, this seems to behave sort of differently than the one I showed you before, right? None of these conventional wisdoms appear to hold up in the data. Okay, so what's going on here, right? What could be the mechanism underlying this relationship, right? Why does this look different than the all-cause effect? Okay, so Durkheim, again, was worried about temperature being correlated with other things that might also affect people's behavior and potentially their suicide risk, right? Particularly, his story was about the intensity of social interaction during warm months, right? So we don't really have seasons in California, so I don't witness this, but I hear from folks who work at other universities where it actually gets cold, and on the first warm day of the year, everyone's out and about, right? Everyone's out, they're wearing shorts, they're biking around, having a good time. Right, so something about social interaction changes when the weather changes, right? So maybe that could be part of what's going on here. People actually drink a lot more alcohol on warm days, and we know that is sometimes associated with different types of violence, right? So it could be that could some social channel could be part of it. There's also an emerging biological or physiological channel. We've talked to folks in the med school about this, and emerging is still sort of the right word. We don't know what's going on here. But we know that some neurotransmitters, specifically serotonin, and I'm sure someone in the room knows way more about this than I do, so I say something stupid, correct me. Serotonin in particular we know is implicated in the body's thermoregulation as well as in regulation of mental affect and human aggression, right? So it's involved in both of these processes in a way that might relate changes in temperature to sort of mental state or mental affect. Okay, but this is a really sort of hard thing to study. So how can we actually differentiate these channels? Here's what we're going to do in this paper. This is sort of a backwards approach. We're going to use mental affect as realized in social media. So I'm sure everyone in here follows Michael on Twitter. I certainly do. This was a screenshot from Michael's Twitter feed a few days ago, right? Michael's tweeted 2,000 times. It turns out people tweet a lot in the US, right? 6,000 tweets per second. And we might think that these tweets actually contain some information about how people are feeling, right? If people are pissed off, they tweet in one way. If they're happy, they tweet in another way. So there might be information in this huge sort of unstructured data stream about mental affect, about people's mental state. Okay, so what we're going to do is we scraped between 2014 and 2015 all the tweets using the Twitter API. I was working with a postdoc, Patrick Bayless, whose job market paper was use this in a different application. And we're going to code these tweets as depressive using two different approaches. One, using an earlier keyword library. So some folks who actually know something about suicide did this with Twitter and showed that Twitter could actually be predictive of suicide rates in the US. So we use their sort of keyword library to code tweets. We also do a homegrown version where we just pull words that we found on word clouds or word mentions on various suicide-related websites. And then we're going to merge these with weather data and do a similar analysis to what I showed you before. So do we see an increase in the use of depressive language on Twitter as we crank up the temperature? And it turns out yes. Either of these codings give you this strong linear upward sloping relationship between depression as measured by Twitter, again, imperfect, right? And the ambient temperature of where the person was tweeting. Okay, so for about 1% to 2% of Twitter users, we know exactly where they were when they were tweeting. So if you use Twitter, you have the option of turning that on or off. Most people turn it off. 1%, 2% of people leave it on, and so these are the tweets from those people. So is that a select sample? Most likely. Here we can just compare Michael to himself over time. We don't have to make comparisons across individuals, and we get a similar answer. So this seems sort of immune to some of the stories about the meta variables you might worry about. Of course, we didn't use Michael's tweets. This. Okay, so to us, this is some indication then that there is this mental component, right? There is, again, this is a little wacky in a sense, right? We're using social media data, but we think it does tell us something about this relationship between changes in temperature and mental state in a way that's consistent with the suicide results that I showed you. Okay, so then what we can do is take this and do sort of the standard exercise where we project out into the future, given projected changes in temperature and precipitation over the next 50 years or over 100 years. We can calculate how many excess suicides we're likely to see with global warming, right? And again, the comparison here is compared to a world in which we warm by, let's say, RCP 8.5 to 2050 versus a world in which we didn't warm at all and suicide rates were held constant at today's rates. Okay. And what we do in this paper is then actually compare the changes in suicide rates, which you get are about 2% in the US and Mexico. We can compare them to published estimates of what other interventions against suicide have done. And this is useful because we can actually calibrate these effect sizes, right? Or these big or small effects. And this is, I think, something that this literature often struggles with is thinking about effect sizes, right? You know, it's easy to run this regression. I'll show you the relationship between temperature and whatever you want, conflict, suicide, agricultural productivity. But is that a big number or a small number? So it turns out with suicide, it's a pretty big number. So a 2% change in the rate is roughly double or triple the effect of an increase in unemployment, a large increase in unemployment on suicide risk. This is something that people have studied for a long time. It's about half the size of huge national suicide programs that have been rolled out across the OECD, right? These are the programs that, like, government-wide programs that we've used, like the sort of flagship programs to reduce suicide in the country. So, of course, temperature is increasing suicide. These are reducing suicide, so you have to reverse the sign. But this climate effect looks really large relative to a lot of the other things we try, or the policy levers we have to try to reduce suicide. Okay, in terms of excess suicide, so this is sort of the map of cumulative suicides, the plot of cumulative suicides by 2050. We calculate about 20,000 cumulative suicides in the US by 2050 and something like 5,000 in Mexico. The population in Mexico is lower. So again, if we just take those numbers and multiply them by the VSL number I told you before, this is already in the low hundreds of billions of dollars in terms of impacts. Already a big number. And that's not accounting for, that's only going to be suicides, that's not accounting for then the likely increase in the mental health burden of people who are increasingly depressed due to hot temperatures but don't actually commit suicide, right? So if you add that stuff up, it's likely, from these estimates, that the overall mental health burden of climate change is likely in the trillions, right? This estimate is, number one, new. Number two, it's not something that's going to show up in those damage functions that I showed you before, right? So here's, even in the US, where we think we're pretty adapted to this stuff, right? Here's a place where impacts could be really, really large, okay? Statistical voyage 1 to the danger zone. Okay, let me show you some evidence from the developing world as well. So, there are a lot of difficulties in doing it, as again, I'm sure folks in the room know, a lot of difficulties in doing these sorts of studies in the developing world. Difficulties on sort of both sides of the equation, right? On the one hand, it's really hard to measure outcomes. We don't have great vital records in many parts of the developing world, right? So we don't measure health outcomes that well, or mortality statistics. On the right-hand side, the other side of the regression, right? We also have pretty bad measures of what's happening with the climate system locally, right? So this is a problem if you want to understand the relationship between health outcomes and the climate system, right? You're fundamentally data constrained. So here's just a plot of to make the weather observation point. Here's the number of sort of high-quality weather stations reporting to the International Climatology Network. So these actually peaked in the sort of around 2000, and many stations since then have gone quiet. Here's a map of the stations. And as you can see, it's sort of hard to see, maybe from where you are, but many countries in sub-Saharan Africa don't have a single high-quality weather station that's reporting to this sort of publicly available international data set, right? So a big problem with measurement. We've done some work to actually use MODIS, which is a satellite that's been up for about 15 years. It has one of the data outputs is a surface temperature data output. It turns out this is a pretty good measure. It's available at a really high spatial scale and a really high sort of temporal cadence. So we've done some work to show that we could actually use this satellite-based measure of temperature. We basically re-estimated response functions in the literature that we knew, so the relationship between temperature and maize productivity in the US. This thing's been really well studied. We sort of know what that looks like. We re-estimate that relationship using MODIS, using our new fancy satellite-based temperature, and we get back exactly what you get back if you use the sort of high-quality station data in the US. So what does this say? This says that we can overcome the challenge on the weather side, at least in part, by using new sources of satellite-based temperature. On the mortality side, what we're going to do is use data from the demographic and health surveys. This is not a new data set. Folks have used this before. It hasn't been applied too much in this setting. So if you're not familiar with the DHS, here's what they look like. There are repeated cross-sectional surveys done in most developing countries around the world. They're geo-referenced, and here's a map of sort of all the DHS surveys that have been done in sub-Saharan Africa over the last 20 years that are in the public domain. As you can see, there's pretty nice spatial coverage. And what's nice is, even though these are cross-sectional surveys, they have this really nice time component, right? So a survey happens in 2015, but what they do is they go in, the sample frame is to go in and ask mothers about their birth history, right? So they go in and ask moms to recall all the kids they had, when the kids were born, and whether or not the kids survived, right? So even in this cross-sectional survey, you're able to reconstruct this time series at a very specific location and at hundreds of thousands of locations around sub-Saharan Africa. So just to show you what that looks like, this is a map or a figure of births in Ethiopia. So the purple dots here are when surveys occurred. But given this time series component that I told you about, the maternal birth history, we can actually reconstruct births back for 20 or 30 years in Ethiopia. Again, subject to some recall error that people imperfectly remember when kids were born. And again, for each of these kids, we have a measure of whether or not they survived, right? So this is a really, really nice data set that can be used for this application, or I think for a lot of sort of environment health applications that folks might be interested in. Last couple of minutes, I'll show you some results here. So here's what we see when we do the similar relationship here. So Africa is pretty warm to start with, so we don't get the really cold temperatures we get in the US. Here is the relationship between temperature, and here we're measuring the outcome is whether the child survived, whether the child died before its first birthday. And unfortunately, infant mortality rates in sub-Saharan Africa are still pretty high. It's about 60 to 70 per 1,000 live births. So 60 to 70 kids die per 1,000 that are born. So that's the outcome, the probability of dying before age 1. And we're relating that to temperature exposure in utero, right? So we know sort of when the kid was born, we know when they were in utero, and we're measuring specific exposure during that in utero period, which a whole host of literature has shown is really important for fetal development and health outcomes. Okay, so what do we see? Across these temperatures, and this is the sort of temperature distribution we see in our data, right? So most of these countries are pretty hot, right? This is Celsius, so places are pretty hot in sub-Saharan Africa, as we know. Pretty linear through most of the domain, right? The marginal effects here are, especially up at the end, they're about 3 to 4% increase in the mortality rate per degree Celsius. So if you compare that to again, this is child mortality. If you compare that to the estimates in the US, it was more, these are like 8 to 10 times as big. So these look a lot like the Indian estimates I showed you before. Okay, so if you scale this up across all of Africa, what this tells you is that for every degree increase in temperature, you get about 50 to 100,000 additional child deaths, right? That is a really, really huge number. So if we want to monetize that, we get into these really tough VSL issues that Denise brought up before, right? If we use the US VSL number, right, multiply 8 million times 100,000, and you get a really, really big number in terms of dollars, right? So these are huge effects. Okay. Last couple slides, and then I'll wrap up. Again, let's think about these conventional wisdoms. Is wealth a mediating factor in this relationship between climate and, in this case, infant mortality? So we can split our data in different ways. We actually have a measure of household wealth in the DHS survey that allows us to do this. So we can split out the response function by poor households and richer households. If you sort of squint your eyes, you can see a slightly flatter slope for the richer guys, but these aren't statistically different. So we find no statistical difference between how rich households respond and how poor households respond to changes in temperature. Finally, we can split up by rural and urban and do something similar. Again, we're still working on this. These aren't confidence intervals. These are different. The lines here are different polynomials. It's not obvious how you want to fit this thing. Sort of no matter what polynomial you run, you get something pretty similar, pretty upward sloping relationship through most of the data. Okay, so just to wrap up here, I think I'm on time. So motivated this more broadly with this statistical voyage into the danger zone, right? This in this sort of broad, persistent view in economics that we're very adaptable to changes in climate, and I showed you some evidence that that's the case. I think that definitely is the case for all-cause mortality, right? So in places where we have a lot of data, like the US, we see a large gradient over income and over time. The effects of climate are just lower in wealthier countries, as best we can tell, and they certainly have gone down over time in the US. So for me, that's really good news. I think that's some evidence of adaptation that's just sort of going on, and that's great. I think the less good news is this is pretty clearly not true for some specific mortality causes that we care about increasingly in this country. And suicide was the one I showed you. And that's probably the case because the effect of temperature on suicide likely occurs through a different mechanism than for all-cause mortality more generally, right? And I showed you some, let's say, suggestive evidence from Twitter that might be the case. And the two results I just showed you in Africa, and this again is work in progress, I think is also not that heartening. So at least at African income level, so within the level of incomes that we observe in Africa, we don't see an obvious income gradient there either. So not a strong adaptation story emerging yet out of the African data. Okay. And finally, the thing I want to leave you with, again, and I think this needs to start informing those damage functions that I showed you before. Again, we're using these damage functions explicitly to make policy decisions, so we need to get those numbers right. What I showed you suggests that the monetized health impacts of just temperature alone are likely to be very, very large, and they could swamp sort of all other sectoral impacts combined. So this health stuff is pretty important. So yeah, I look forward to your comments and questions. Thanks.
So I'm a little bit confused about VSL. In that, I'm not familiar with the statistics, so this may just be an ignorant question, but how is it related to productivity or any other output factor as opposed to a humanistic factor?
So it's related strongly to income. So in the sense that we assign the same DSL to anyone in the U.S. basically, and so we try to, or the way it's typically done is we calculate a DSL for like any American life, and again that's based on an aggregate estimate of our willingness to pay to not die, estimated in different ways. So the bike helmet was a cute example, but that's basically how these studies are done, right? So how much do we spend on things that make it less likely for us to die? And based on whatever that thing is, the estimated likelihood that reduces our likelihood of dying, we can compare how much we spent to that change in probability to back out our willingness to pay to not die. So I think the PyCon example is one of them.
Thanks. So I'd like to ask a more wide-ranging question. So let's suppose I'm a decision maker and I see this conclusion that these monetized health impacts are likely to be very large from all these various different factors, but I want to know about my opportunity costs. So is there work that's, say, comparing, so there are a lot of advantages to mitigating, which are not just health impacts, obviously, but if, let's say I'm concerned just about health impacts, are there studies which look at comparing direct health interventions with the health impacts you would get by mitigating? Presumably, on the second one, they would be a lot smaller, but do we have any idea of what kind of comparisons?
Yeah, so that was sort of this motivation for the suicide thing I showed you, right? So this is looking at sort of impacts of policies. So this was our sort of crass attempt at comparing, what climate's going to do to the other things that we think affect suicide, that have been measured to affect suicide. So this I think starts to answer your question, right? You don't see costs on here, right? So we're not doing the cost question, which is, all right, so mitigation is going to buy you 2% in terms of suicide. National suicide prevention programs are going to buy you 6%, right? But then you have to worry about the cost. I don't know what the cost is. So much to work on. Yeah, we're focused on the impacts.
Actually, this is a perfect slide for my question.
Cool.
So I was really interested in how temperature increases seem to lead to increased suicides. But I'm wondering about the projection into the future, because you could imagine that as climate impacts become larger and people's beach houses get washed to sea, or there's droughts that cause crop failures, that people will get depressed from these larger scale climatic effects, and suicide rates may go up.
Right.
So I'm just wondering if you would think this would be a lower end estimate of the effect, and how you would include the larger sort of systemic climate implications in the future.
Yeah, that's a great question, and it's a fundamental problem in all of this stuff. So I'm giving you a number of excess deaths, right? And that number is going to depend heavily on what I assume the base rate is, right? And this base rate could be affected by all sorts of things. It could be affected just by secular declines or increases in the suicide rate. So in the US, we've seen an increasing suicide rate, right? If that thing keeps going up, we're going to increase that by some percentage, right? So as the base rate goes up, the amount we actually increase that by is larger, right? So if I assume a higher base rate, then this number is going to go up just for no other reason than assuming a different secular trend, right? So yeah, we don't know. I think the best thing we can do in this setting is to run this under different, maybe plausible assumptions of what changes in that base rate might look like, and redo this. I think you're right. I think there are a lot of reasons you might think that this could be a lower bound on potential impacts.
I wonder if you could look at suicide rates in areas that are affected by strong events like Hurricane Sandy.
Yeah.
It was like on the coast of New Jersey, right?
Yeah, sure. People have done that, the effect of natural disasters on depression and suicide. Anyone know these papers? No, not like hurricanes and stuff. I do remember seeing papers on this. I forget what they found. I think your intuition, I'm sure, is right there. Yeah, we should look at that.
Questions? Go back.
Yeah, I have a question that when I listen to presentations by economists, I have a slight disjunction in me, one of which is the natural scientists sort of worrying about systemic effects, system change, and how we're going to cope with that. And kind of like nice graphs which move quite smoothly. And I think you did at the beginning, you did quite an excellent job of showing us the kind of the problem in effect of the economic models as they stand. My question is really how much of this kind of work would it take to change the way that those kind of look in broad terms, which is like the effect is, well, it's sort of we can pay our way out of it, or we can make some sensible choices, actually all the way up to 6 degrees is kind of the message they give. Does that make sense?
Make sure I understand your question. So is your question about how to use this in a decision-making process? Sorry.
No, and I guess my question is that it seemed to me that the kind of overall narrative of what you were trying to say was that this kind of work was really informing those cost functions in a way that was kind of unpicking some of their assumptions and would make them look quite different. Right. Well, a couple of studies isn't going to do that, and I was wondering, what is the scale of the kind of activities that you're showing that would actually change those to look fundamentally different?
I see. So at a sort of basic level, we're trying to work with some of the folks who write down these models to better integrate these sorts of estimates into those modeling exercises. That's sort of a boring response to your question. We're trying to work directly with these guys to update the damage functions. I think more broadly, I mean, there is a fundamental belief in economics that humans are imminently adaptable, right? And this is just, I think, something that economists have not been great about, and not been great about being true to the data and looking at where people have adapted well and where they haven't, right? And actually recognizing that often adaptation is really hard and really costly. And even in places where we do adapt, it's because we made very large investments and those cost money, right? I think my discipline has not been great about thinking about that problem. So I think that the broader integration of these sorts of results into the thinking in economics is going to take long, because it goes at sort of fundamental, again, conventional wisdoms of the discipline.
Marshall, could you put some of the numbers in context? At the beginning, you started with that classical comparison of the few percent cumulative damages versus the total economic growth over 50 or 100 years. So what happens if you then come to the end of the talk and you talk about the numbers in terms of mortality, just those costs, which are much higher than the individual sectoral costs that add up to the several percent? How does that change the picture? Are we talking about an order of magnitude change? And I know projecting a long way in the future is not what you're doing here, but still, sensitivity.
Yeah.
Be brave here. Let's have a
Okay. Let's see. So it again hinges heavily on your assumption about how fast the economy is going to grow in the absence of climate change. So current world economy is 17 trillion. And so if we grow at 1%, by 2100, we're going to be at 40 trillion, right? So our estimates here would be that, and again, we haven't monetized the health burden in sub-Saharan Africa, but it would be probably, I'm going to guess, at least a doubling of the numbers I showed you before, just adding in the health impacts alone. That's a guess.
Okay, so
I think that's right order of magnitude.
Okay, so when you add everything together, it's still going to be, a chunk of the growth, but maybe the 10% level instead of the 1% level or something like that.
Yeah.
Thank you for the wonderful talk. If you were going to look at other health impacts besides suicide, what would be number 2 or number 3? What would be the best candidates to look at, like, for example, stroke or heart disease? And what would be your sources to look at that, and why? I mean, how much more difficult is it to get at those sorts of diseases, given that medical records often don't, there's no diagnostic for climate change at this point.
Right.
So.
So historically, we could have a shot at it. So in the mortality statistics, again, they have sort of a estimate, really, of how someone died, right? So in the U.S., you actually know for each individual if there's sort of a cause of death associated with their death. Suicide, I think, is easier to sort of ascertain than some of the more specific. So is it ischemic heart disease? Is it, some respiratory failure? I mean, I think, there are good protocols for understanding that, but it's still imperfect. So I think even in historical data in the U.S., we can have a shot at looking at some of these different things. Some colleagues just bought this huge, that I have at Stanford, just bought this huge health insurance claims data set, which actually should allow us to look sort of more directly at what people are spending money on in response to climate shocks. So our hope is that it would give us more granularity in that. Those data sets don't exist for most of the developing world, and so it's hard to do. So I showed you these effects for child mortality. We can't measure adult mortality in those data sets. All we see are kids, right? So is the adult mortality different somehow from child mortality? That India result I showed you, they see very small effects on child mortality, right? Their adult mortality effects are actually bigger than the child mortality effects. Is that true in Africa? I mean, I don't think we know.
Last question.
So when it comes to comparing overall mortality data to temperature, I've heard some, arguments against some of the correlation that when you have a heat wave, it just causes people to die maybe a few days earlier than they otherwise would. So when you're looking at the suicide rate and correlating with the daily temperature, how do you, and I don't have an econometric background, so maybe it's a stupid question, but how do you pull that out from saying, okay, maybe in a given year, a certain number of people might be likely to commit suicide, and the hot season just kind of instigates that?
Yeah, no, this is a fundamental question, and I glazed over it in our results, but you're absolutely right, and it's something you have to worry about. So the terrible sort of economist term for this is harvesting, right? I told you, a lot of odious things come out of my discipline, right? Basically, so the idea is you have people who are going to commit suicide either way. You get a heat wave, they commit suicide a little bit earlier than they would have otherwise. But if you just regress suicide on daily temperature, it looks like you see this big spike, but a lot of them are not additional, right? They just happened earlier. So what you can do then is not just look at the effective temperature on that day, you can look at the effective temperature over the last 30 days or 100 days, right? And you can add up all those effects, and those will account for the displacement that you're worried about. So there's sort of straightforward techniques to deal with that, but it's absolutely something you have to keep in mind. So everything I'm showing you here accounts for any of the displacement effect.
Okay.
So in the US, we see no displacement at all. In Mexico, we actually see a lot of displacement. So about half of the immediate effect in Mexico looks like displacement. We don't understand why.
So let's thank Marshall once again for a talk that we did.
Thanks.